All right, so for our lab, this rods and cones lab, we talked about it a bit in or on Monday, and we are going to kind of dig into this. Normally, what this lab is about, I can stop sharing this now. Normally, when we do this lab, this is a lab that is about kind of taking off the training wheels in some level of like designing a lab. Like up to this point, every lab you've been doing, there has been just very specific instructions. Here's the materials, the methods, and you follow along. As you probably noticed for this one, there is no methods in the lab notebook. And so what we're going to do is, I'm going to give you the basic objective, which is the one we've already talked about on Monday. But then we'll all kind of discuss together, how can we actually design an experiment that is going to test our hypothesis? And then we can also then talk about what are all the sources of variability. So like if you run an experiment and you haven't really thought about sources of variability ahead of time, you're often going to end up with a bunch of data you can't use because then the source of variability has just as much effect on your data as anything you are actually interested in. So what we're going to do right now is kind of review again what is our objective for today's lab. Review kind of the basic hypothesis that we actually did mention last time, and then work together to come up with how to approach the methods. And then we'll put you all into breakout rooms, like in groups of 4. And you will actually have to, in your lab notebook, and I know nobody's forgot their lab notebook because you're all at home, and you're going to actually, physically write out your objective, your hypothesis, and then in your groups, you're going to come up and converge on your actual methods. Like here's the procedure, step 1, step 2, step 3, step 4, step 5, step 6. And you're going to all, obviously for any particular group, it's all going to be, the same basic thing. But you're going to write that as well in your lab notebooks. I'll give you like about a half hour or so to work in your groups to actually, work out the details of your methods, actually write it in. I actually created a new little thing in the rods and cones module where you're going to actually upload, because I can't go around with a stamp and make sure everybody's looks good. So instead, you're going to do another thing where you take a little snapshot and upload your objective, hypothesis, methods up into the rods and cones module in the Canvas. And then once we have everybody at that point where everybody's on the same page, then we can do the next step and kind of pretend we're actually doing the experiment. And I actually have data that we have from last semester, and we can look at like what is that? What did we find? What does that mean? And that kind of sets you up for the, the important part of actually interpreting the data and seeing does it support your hypothesis and all that. But a big part of today's lab is kind of going through the mechanics of how do you actually design an experiment? What do you think about when you're designing an experiment? How do you try to make sure that your data is useful, even though sources of variability can often trip you up? So let me go back to my whiteboard. So does anybody kind of remember the objective
Sorry,
that we came up with at the end of last class?
can we use blue pen or does it have to be black?
I think blue should work.
Okay, thank you.
Yeah, so does anybody remember of what we were talking about? We talked about differences between rods and cones. When we talked about, rods versus cones, what are some of the differences between rods and cones?
Low acuity and high acuity.
So rods were low acuity, cones were high acuity. What's another one?
Rods are monochromatic. Cones.
Monochrome versus color. And hopefully both of these are things that you actually saw when you did that little exercise. And you put the lights way down low, you lose the color. If you have a piece of paper in front of you, you could read it just fine with bright light using cones. But with the rods, it just looks kind of like you can see there's probably something on the paper, but you have no idea what the words actually say. So things like the acuity differences are things that are easy to tell just by kind of noticing as you go from dim light into bright light. Same thing, colors fade away in dim light. They snap when you get into the bright light. What are other differences between rods and cones?
Response time?
So one was the response time. We talked about rods are slower response. Cones are quicker, faster response. This is something that we would not be able to see just in kind of normal noticing things, but it's actually something we're going to look at in much more detail for the rest of this afternoon, or this morning, I should say. And I think this is one of these things where you're going to have to believe the data that we're going to be using actually is real data. It's obviously not as fun when we're not all actually like hopping up on desks and dropping sticks and doing all sorts of fun stuff. But the actual data is going to be real data. So it's not data we made up and just to kind of prove a point. It's actually going to be real data. What are another huge difference between rods and cones that we haven't put on this chart yet?
Rods are active in dim light and cones are active in bright light.
Exactly, dim versus bright. Right, so I mean, this is going to be one of the main ways if you want to know whether you're using your rods or using your cones. You can do that by changing the brightness in the room. If you're in very dim light, cones can't operate in really dim light, so you've got to be in the rod vision. In really bright light, we know the cones work fine and the rods get bleached. So these get bleached in bright light. By bleached, it means all the retinal gets flipped. So you don't have a bunch of cis retinal ready to flip to detect the light, right? So if you overwhelm all of the retinal and opsin, so all of it is kind of triggered, then you don't have anything left to tell if there's some more new light coming in. So in really bright light, that's what that's what it means by saying that the rods are getting bleached, is all of the retinal and opsin has been triggered. The retinal and opsin in rods, sometimes they call rhodopsin. It used to be called visual purple, actually, because when people would first try to understand the eye, they would take animal eyes and they would find this purpley stuff in the retina that would bleach, that would change colors as soon as it got exposed to light. It was actually the rhodopsin, which is actually the opsin in the retinal. But sometimes you'll still see it called visual purple. It's just the light sensitive pigments in the retina. So this is kind of the background. Cones, we know they're on if we are in bright light. Rods, we know we're using them if we're in dim light. We know if we're in bright light, the rods are getting bleached, which we actually do have to worry about because what did you notice for the people that actually did the exercise where you walked turned off all the lights? Could you see everything in using rods right away?
No.
No. What was your first experience when you turned the lights off?
Well, I'm older, so it went pitch black.
Right. It's not about being older. For anybody, it would go pretty much pitch black. Because as soon as you shut off the lights from bright light, you're not in cones anymore, but the rods are still bleached. They don't have the ability to respond yet. So you don't have your cones working because it's not bright enough, but the rods aren't working because it takes some time to recover from getting bleached. The recovery takes usually at least 5 to 10 minutes. You can keep getting more and more of your night vision coming on for like up to 20 minutes after the lights are off. So
Does age affect how fast you can see an image in the dark or the recovery period?
that I don't know. Um, it wouldn't surprise me. Almost everything gets worse as you get older, but I've never actually heard of that in particular. So there's lots of things we can specifically say get worse as you get older, but that one I'm not so sure is a problem. So what we're going to be playing around with in today's lab is the fact that we can shift back and forth between rod vision and cone vision by going back and forth between bright and dim and bright light. And we know already this acuity and the color stuff. If you haven't done that, I actually changed the due date to Friday. So please do that actual personal experience of going into the dim versus the bright and describing. It's just like a few sentences you'll type into the little Canvas assignment. Describe your experience. Because I do want you to have, even though we're not in lab, I want you to still have some personal experience of this stuff because it's more fun. This response thing that's the thing we're going to be able to play with today. As we go between dim and bright, which takes us between rods and cones, we should be able to see some evidence of the slower and faster response. So we're going to do then is we're going to look at a visual reflex. Any kind of reflex, there's some stimulus. But if it's a visual reflex, it's going to be a visual stimulus. There's always going to be some kind of integration. And there's always going to be some kind of a response. So this is what we're going to be playing with. There's a visual stimulus and there's a response. There's going to be some time that it takes from when the visual stimulus occurs to when the response happens. So an objective then, and I'll help you out here. If we know that the brightness of the light changes whether we're using rods or cones, and whether we're using rods or cones affects the speed that you are actually responding to the visual information, then it would be interesting to see, how does, brightness, affect the speed of a visual reflex. So this is going to be the core of everything we're doing today. We have this question. Again, objective is always going to be a question. How does the brightness of the light, I should say, brightness of the light affect the speed of a visual reflex? So what is our, remember the objective also includes our dependent and independent variables. So what is our independent variable in this case here?
Brightness.
Yeah, so we have our independent variable is going to be the brightness of our light. And what about our dependent variable?
The speed?
Yes, it's going to be the speed of the reflex. So this is at the core. So brightness is something that's actually really easy to adjust. Normally, if we were in lab, I would just be changing. We have the switches on the wall. I also have these special illuminators. We can actually make the room very dim to where you can barely see anything. We can make it super bright by turning on all of the different lights. So adjusting the independent variable, the brightness, is going to be very easy. We just use it by changing lights. And in fact, we're going to use 3 different values. We're going to go, so brightness, normally what I do is I have brightness going from 1 to 5. And just by adjusting the lights, we can have like super dim to medium to bright to super bright. So just to kind of quantify things so we can actually, if we were doing a more formal experiment, we would probably do brightness in lumens. But for our purposes, this is just fine. We're going to have brightness measured in these arbitrary units that I'm just calling brightness units. 1 is the dimmest, where you could just barely see stuff. 5 is like all the lights on, the brightest we can make it. So that's going to be easy. This part's going to be a little trickier. So to measure the speed of a visual reflex, we need a visual reflex. Does anybody have any suggestions for what we could use as a visual reflex for this experiment to like see if brightness affects its speed?
Could we use our phone lights?
So what would the reflex be?
Or would we look at our pupil? Dilation.
Yeah, so that would be something you could do. That would be a visual reflex, actually. Yeah, there's some like change in light, and you'd see some change in the iris. That would be really tricky for us to actually measure. You'd need to have some fancy stuff measuring the looking at your pupil and quantifying the diameter and stuff. So what we want to do is something that's going to be simple. Right? We could also have something where something moves and then you push a button and it calculates how long between when you saw it move and you push the button. And the other thing I will say that although we are going to see differences in speed, the differences are not huge. The differences are in fractions of a second. So we want to design some experiment where we can measure things that differ by fractions of a second, and yet we're going to be using kind of very low tech kind of materials. Like so, because basically in this lab we're going to be using rulers and sticks, and it's actually still going to be able to let us find some really cool stuff. So, so this I don't know if this is like one of the classic. I don't know if people have done this in the past, where you like take. It's like something we used to do. You like have like a dollar bill, and then you have somebody put their fingers, and then you drop it, and if they can grab it, they get to keep it. Has anybody ever done that? If you haven't, you should do it. It's way harder than it looks. Usually it's a pretty safe bet that you're not going to lose your dollar. By the time they see it falling and they try to grab it, it's already past their fingers and they've actually haven't got it. Every once in a while, there's people that got it. But usually, so this is a visual reflex though. You know, you're poised, ready to go, and as soon as you see it drop, you try to grab it. And that is a visual reflex, and we're going to adapt that in order to do our lab today. So the basic idea is going to be, and again, another reason why I feel kind of bad for you, this is actually kind of fun, because somebody gets to stand up on the tables. And even as it gets really dark, it's actually really fun standing up on the desks in the dark. Um, I think at least. And you're like holding a stick. We've got some little mark on there so it's easy to see. You're going to have like your subject who's standing on the ground here, looking at that mark. They're going to have their hand. Again, you don't want to actually be touching it though, because if you're touching it, it's no longer a visual stimulus. It's now a tactile, right? You're going to actually feel it. So they're here. Basically, this person here is going to drop the stick. The stick will drop. So if I kind of, so this person here will grab the stick. And so the stick is going to fall a certain distance by the time the person grabs it. They're going to see it. That's going to be how they know it's time to grab as it starts falling. But then it's going to fall a certain distance by the time they catch it. So does that make sense? Is everybody kind of on board with that? Somebody's standing on the desk and they drop the stick, and as soon as the subject sees the stick dropping, they try to grab it, and it will have fallen a certain amount by the time they grab it. What's nice about this is if you've taken physics, you probably know there's a really simple relationship between how far does something fall due to gravity in a certain amount of time. So what we can do is we can measure this distance really easy just by using a ruler. It will have fallen a reasonable amount of distance that you can actually measure it using a regular kind of ruler. If we just measure it in centimeters or whatever, it'll be easy. And in physics, basically x, which is distance, 1/2 gt squared. G is acceleration due to gravity. It's 9.8 meters per second squared. T is time in seconds. This is distance in meters. So it's just a really simple math thing. Basically, I want the time. So I have the distance here that it fell. I multiply it times 2, right? Because I have to take this and move it over. I have to divide by g, put that on the bottom. In fact, let's just, since I know g is 9.8, I'm just going to write 9.8. And because this is a square, I'm going to have to take the square root of that. And that's going to be time in seconds. And this is the distance it fell in meters. So you're going to have to make sure you convert whatever your distance is from, if you measure it in centimeters into meters. But so this is, often people talk about elegant experimental design, like elegance actually being one of the values that you have when you're designing an experiment. The simpler you can make it, the better, the less things to go wrong. This is like really freaking simple. You just drop a stick and try to grab it, but we actually are going to be able to get a really accurate measure of how much time did it take from when they saw it starting to drop to when they actually grabbed it. So the time of the reflex is going to be really easy to measure. All we do is we initially measure the distance, but then a simple math conversion, and we actually have the time in seconds. So in general, I mean, again, since we're not designing our own experiments, it's not such an issue anymore, but if we were designing our own experiments for the independent research project, or in the future, whenever you're doing stuff, the simpler you can make it, the better, because the more direct your answers are going to be, the less things you have to worry about going wrong or influencing what happened. So are there any questions about this basic task and why it's a nice way to give us the timing of a visual reflex? Okay, so next, oh, these are all still here. All right, so back to here, we had our objective. How does the brightness affect the speed of a visual reflex? So what's the second part we usually do after we come up with the objective?
A hypothesis?
Exactly, hypothesis. So objective, how does brightness of light affect speed of visual reflex? Now our hypothesis. Does anybody want to volunteer a hypothesis? So again, we have our independent variable, brightness of the light, dependent variable, speed of the reflex. So what do you expect that relation to be and why?
The brighter the light, the quicker the reaction rate.
So, right, does that make, right? Does everybody hear that? The brighter the light, the faster the faster the reaction rate, the faster the speed of the reflex. So that's a good what? And then we need to add in the why. Why does that make sense?
Because the cones are operating in bright light and they're faster.
Exactly.
Reaction.
Is everybody here, Anne? You know, she's got this why. You know, if the brighter the light, the more you're going to be using your cones. Dim light are going to be using rods. And we know that cones are faster than rods. So bright light, which using cones, is going to be faster than dimmer light, which is using rods, because cones process images faster than rods. So that is, I'm not going to write it here because I want you to actually write it down. But that is basically, you know, perfect for a hypothesis. You know, what you expect to find, that relationship, the brighter the light, the faster the reflex. Why? Because as we go from rods into cones, dim to bright is rods into cones, and means slower processing to faster processing. So that should be in your lab notebook. This is kind of your objective, your hypothesis. Then sources of variability. This is super important if you're designing an experiment, is to really think about sources of variability. So let's just throw some out there. What are some of the things that are going to affect this experiment if you're actually doing it? We're dropping a stick as we vary the light from dim to bright. what are some of the things that are going to affect our results that we probably want to think about before we actually do this?
The brightness of the light.
So that's not going to be, so that's going to actually be controlled. That is the one thing that's going to be our dependent variable. I mean, normally I would be in control of the light, making it dimmer, making it brighter. So that's not going to be so much a source of variability. It could be like homogeneity. You know, we'd want to make sure that the light is the same across the whole room rather than having, you know, sometimes it's hard to make the brightness the same across the whole room. But in general, the brightness of the light is something we're going to trust is actually controlled. So this is going to be stuff that might affect our results, but we're not explicitly controlling.
Is there fall today?
Say that again, Megan.
Yeah.
Sorry. Wrong
So-
question.
A source of variability. So what's another source of?
Everyone's individual vision or age or
Yeah,
what,
so
anything.
vision. So totally, right? Your, you know, visual acuity, right? If somebody just has really crappy vision and they're not wearing their glasses, that's going to totally affect whether or not they even see this stick falling. So any kind of experiment like this that is assuming that you can see well, usually in the criteria for your subjects, they will always say normal or corrected to normal vision. You know, so that is something that you have to have explicitly in your procedure. Otherwise, when you're interpreting the data later, someone could say like, how do I know I trust this? I mean, maybe they were just, they don't see that well. That's why we have differences between these subjects. It wasn't about the brightness. It's just somebody has really bad visual acuity and they weren't wearing their glasses or something. But if we say ahead of time, nope, your subject has to have normal or corrected to normal vision, then I have now controlled for that source of variability. So this is like why you have to do this ahead of time. If you don't do this ahead of time and you just do the experiment and then realize, oh, I should have made sure that my subject had normal or corrected to normal vision, but because I didn't, I can't really trust that that was true. So how about another? What's another source of variability?
With someone's like hand-eye coordination or like just natural reflexes.
Yeah,
feeling?
kind of natural differences in reflex speed. So how can we deal with that? How can we deal with the fact that, you know, I've seen this all the time. There's some people that, you know, you kind of want them on your team of like post-apocalyptic world where you're just trying to grab animals for food or something. Other people are kind of more, whoa, something's moving, I'm going to try to grab it. So how do we bring that into account in our experimental design?
Could you do a control where you're not worried about light and just seeing how they catch it?
Or more, what we're going to do, if you can just do all the conditions on the same person, then it doesn't really matter if they are super twitchy or maybe more slow, but you can still see how does that one person vary in dim light versus bright light. So like the integration is the same, right? So the, you know, the middle of that reflex is not changing because it's just the same person, but you're still getting to change rods versus cones on the stimulus side. You know, and the other thing you do is you end up getting more than one subject, right? If you get more than one subject and you average across many subjects, that often is also another way to deal with individual variation across. We saw that in the nerve stimulation lab. If you looked at any one particular person, it didn't necessarily look exactly like you expected. Like frequency versus threshold or something. But when you averaged across everybody, it actually looked really nice. So, but that's the source of variability, natural differences and reflexes in an individual. So we want to make sure we get all 5 conditions, super dim to super bright, on the same person, so we can compare across that same person. And then also get a number of people to make sure we see similar trends across all the different people as well. What are some other sources of variability?
Could how you switch between conditions have an impact? Say, like if you went from brightest to dimmest and didn't give the eyes enough time to adjust from the bleaching?
Totally. So dark adaptation. So if you are going from a brighter light to a dimmer light, your rods aren't working right away. So if you go from bright to dark, brighter to darker, you need to wait, at least 5 minutes before you get any data, because otherwise you can't trust that the rods are actually working, right? So this brings up an interesting question. What if we just started in the dark, or I should say, let's start in super dim and go to super bright and just get our data first here. So here we would never have to worry about dark adaptation. If we're always going from dimmer to brighter, we would not have to worry about dark adaptation. But there's a huge problem with doing the experiment like this. Why, like if we started like, trial 1 to trial 5, why do we so not want to do this? What's another source of variability if you're like checking the speed of how well you do some task?
They will have been practicing it.
Totally, right? Another huge source of variability is practice. Right? The more you do something, usually the better you get. So if we go, whoops, if we did it like this, just started trial 1 with super dim, trial 5 with super bright, and let's say we got some result like this, was like, dim to bright and speed, or, the time, I should say, time of the reaction. And it was like this, it's like, oh, take a look. The brighter it got, the less time it took them to grab the stick. And you'd say, haha, that's supporting my hypothesis that brighter light is faster reaction. But then somebody could come and say, like, sure, how do I know this? Like, by the time they were in the brightest light, they've also been doing it the most amount of times. How do we know this isn't just about practice? They could be getting better here because they just had more practice. That's why they're faster. It has nothing to do with the light. So you have to really be careful that if you have 2 variables that, especially that can both have an important effect on your dependent variable here, you need to disconnect them. If your brightness and your trial number, your practice, move together perfectly in lockstep, there's no way to tell the difference of the effect of one from the other. So how are we going to make sure that we know that it's not just practice that is affecting the time and that it's actually the lighting? Is this making sense here? We need to make sure brightness and practice, which we're, kind of the trial number, are independent. So when we're analyzing our data, we can see, is practice make for faster reaction times, or does brightness make for faster reaction times? But we need to be able to do that independently, separately, versus in the situation I just showed you here. If you have brightness and trial number both moving together, 1, 1, 2, 2, 3, 3, 3, 3, 4, 4, 5, 5, there's no way to separate them. So how can we do it?
Would you just mix the trials up so it doesn't go from dimmest to brightest, but like kind of in a random order?
Exactly. Exactly. So that is exactly what we do. So you have like trial number. And then the brightness of that trial, you have to make sure that they are randomized. If we were doing this lab together, at this point, we would all just have you guys come up with brightnesses for each trial. And then we would actually do the experiment. Because we're having to use data that exists, I'm just going to tell you what we figured, what we chose last semester. Last semester, just people decided, let's start with 3, the medium brightness, then went to 5, which was super bright. Then it went to 2, which is the dim. Then we went to 4, which was bright. Then we went to 1, which was super dim. So now you could analyze your data. Let's look at trial number versus reaction time. Or we could look at brightness versus reaction time, and they'll be separate. We'll be able to see, does trial number seem to make more of a difference, or does brightness make more of a difference? So is this making sense? We'll talk more about this as well once we get our data and actually look at how we analyze it. This is going to be an important part of your discussion, is making sure that if you're going to say like, oh yeah, the data supports our hypothesis about brightness affecting reaction speed, what evidence do we have that it wasn't just practice? And we are going to have evidence about practice versus brightness because we randomize this. So you should write this. Yeah, you should write this down right now, because when you're making your protocols in a few moments, you need to make sure part of your protocol is this specific brightness for each trial, because that's what your data is going to be reflecting. What are more sources of variability? Think about the jumping lab. Every time you jump, do you jump the exact same height? Every time you try to grab a stick, even under the exact same conditions, are you going to grab it exactly as fast?
You should do more than one, at least 3 trials and average it.
Right, exactly. It's going to be, so another source of variability is, you know, individual performance, varies from trial to trial. So we're going to probably want to do like 3 trials in any condition and average them, right? Right, just like we did for the jumping lab. If you just measured once, how do I know that that wasn't just a particularly good or a particularly bad trial? Instead, you want to take a few trials and see if average them and say that's kind of our real number. What are other sources of variability? Anybody? So I'm going to say we want to make sure that it's a visual reflex. So in order to make sure it's a visual reflex, we're going to have to make sure like they're not actually touching the stick, right? So when we're writing our procedure, we want to make sure that they're just using their eyes, no tactile. So in your procedure, you need to be explicit, holding your hand close to the stick, but not touching it, because otherwise it would be a tactile reflex. You also don't want them to like anticipate. Right? If you say, okay, ready, go, they might just be grabbing because of go or because of your little twitch or whatever. So how do we make sure that it's the visual reflex and not like some other clue that is triggering the reflex? You kind of think about what we did with electrical stimulation lab. We wanted to make sure that they felt it when they felt it, but they didn't like just respond to you clicking, or that, but they didn't get bored either.
Conversing with the subject and, not keeping their mind off the procedure.
You kind of want them to have their mind on it. You want them to stay focused. If they start mind wandering, then they're gonna like miss it when it starts falling.
You can tell them that you're going to do it within like 10 seconds, but not exactly when.
Yeah, exactly. Kind of like we did with the electrical stimulation. This kind of window. Tell them, get ready. And it might be 5 to 10 seconds. So they don't know exactly when it's going to start, but it's short enough that they can stay focused and not start mind wandering, but they don't know exactly. So it's not like go and they grabbed because you said go rather than they saw it move. So we can kind of try to ensure that it's a visual reflex by making sure that they're not touching it, giving them kind of a window so they're not anticipating it or responding to like some other thing like you're talking or whatever. What are other sources of variability? I'll just mention another one here. If we go back to this equation relating the time to the falling with respect to gravity is assuming that it's acceleration just due to gravity and not due to somebody pushing or on the stick to start with. So when you drop the stick here, this also has to be in your procedure. You need to make sure that there is no initial velocity. If you push the stick down a bit as you start, then that formula doesn't work anymore. Or if you pull up a bit and kind of loft it up, the formula doesn't work anymore. So the formula is only going to give you the time compared to distance if you basically lightly held it and just let it drop and start accelerating purely due to gravity. So does that make sense? So any questions about all of this? So what I'm going to do right now is just kind of show you what this looks like. I'm going to Hold on a second. All right, I'm going to shift into. All right, so I created a channel, a YouTube channel for human physiology, which you can probably sign up for. This is where I'm going to be posting videos that have to do with our class. I'm going to also be posting edited versions. Like on ConferZoom, there are actually recordings of everything that you can access. If there's things that need to get edited, I'll put them up here. So this is going to be the kind of YouTube home of human physiology for this semester. One of the things that I have up here is the stick drop task. I'm assuming you can all see this. Does everybody see this happening?
Yeah.
I don't hear.
Yeah, I can see it.
Yes.
Can people hear it?
No.
No.
Oh. So what I would say after this is done, you should actually view this in person on YouTube, because on YouTube there's actually talking. This is basically, I'm saying, all right, window, go, and as soon as it starts dropping, I'm yapping at you all. I'll have to figure out how to get the audio going here. I'm not sure why there's no audio. Come on. So I'm basically saying blah, 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 blah. I don't even remember exactly. So here, oh, so I'm gonna, yeah, you'll read this and it'll make more sense once you actually hear it with the words. Come on, drop it, David. Oh, here I'm saying don't give it an initial upward or downward thing, because that's going to mess up the, and then I actually totally spazzed. So we're going to measure the distance to calculate the time, using our cool little, equation. So then now I think I'm going to finally show what it looks like to drop it. And Becky is being super patient here while I'm going yap, 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 yap. Come on, drop the stick. Okay, here she goes. All right, she's gonna take the web of her finger, because you want to really make sure, and also another thing, source of variability, just comfort. Probably want to make sure you're holding the stick at a comfortable level for your subject. And then make sure the web of the finger is right. In fact, maybe I should go back here for a second. You want to make sure that the web of the finger, oh, come on. See how the web of her finger is right at that black line. So that way, when she grabs it, we can measure the distance accurately from wherever the black line is now to wherever the web of her finger is. So you're going to have to make sure in your procedure, that's another part of your procedure. Have your subjects stand there, web of their finger at that line, and then have the stick drop. Wherever they grab it, measure the distance from where the line is now to where the web of their finger is after they've dropped it or caught it. So here she goes. So you would measure from wherever the stick was now to where it started. You probably want to practice a few times, but then you're going to take 3 different ones in each of the 3 conditions. Here she's kind of showing the measuring. Normally you would have another person. Again, we were doing this after the shelter in place already, so we thought it would be like kind of bad modeling to have us too close here. But normally you couldn't really measure your own thing that easy. So we're having trouble getting this is Tina's on the other side here. You'll see her in some of the other videos later, but we're all like doing our best. And so basically, and if it's in the dark, what? let's stop this. So another thing that I'm going to show you on our, hold on a sec. There we go, course modules. Okay, I'm going to share, new share. Okay. So this, if you would go in here, this is where you have rods and cones lab and accessory material. This is where you are going to find the link to the YouTube thing that we just saw. This here is showing you kind of what the room would normally look like in dim, super bright, just to give you a sense of what those conditions really look like. You know, I actually just went into Photoshop and messed it with it a bit, but this is kind of what it looks like when you're going from super dim. And so you'd basically do the 3 catches under these 5 different brightness conditions.
What are you doing?
What? What's that? So are there any questions about the basic idea here? All right, so what we're going to do now is we're going to get into breakout rooms. I could either just have it randomly assign you into breakout rooms, or do you have groups that you want to stay in right now?
Can we stay in our groups, our original groups?
You can. So you have to kind of tell me. I'm going to write them down right now, and then as we do this, I'm going to put you into the rooms. In fact, so I'm going into breakout rooms. There's going to be manually. Okay, I'm creating the rooms. I'm going to assign people into breakout rooms. I'm going to still be here, so I'm assuming you can get out of your breakout room if you want. So if you want to ask me questions, you're going to have a half an hour. So basically, from now until 11:30, you're going to be working with your partners to do your objective, hypothesis, and method. And then I actually included another thing here, which you're going to see courses, module, where's the modules go? Hey. Here under the rods and cones, there's, oh my God, rods and cones, objective, hypothesis, and procedure. So you're going to take a picture of the stuff in your own personal lab book in your handwriting, and you're going to upload it up to here. So like a half hour from now. Does a half hour seem right, or do you think like 45 minutes sounds better? Does a half hour seem like it'll work for you?
Yeah. 45 minutes sounds way better.
So we can say, so at a quarter to, yeah, so at a quarter to 12, we are going to come back. And again, I'll be here if you have questions, but I'm going to start assigning you into breakout rooms now. So if you just tell me the 3 or 4 people, and I will start putting you into the rooms. So So again, normally we would have actually been doing the experiment after you wrote down your procedure and get the data. Instead, we're going to use the data that was recorded by students last semester. And so here it is. So what you're seeing here, if I can like zoom in a little bit, maybe. So here we have the trial number, trial 1, 2, 3, 4, 5. The light level that we had, again, we were randomizing. So the first trial was the medium, the second trial was super bright, the third trial was dim, fourth trial was the bright, and again, if you want to remember what that looked like on that, I showed you that picture. In fact, and doobie-doo, share. That's what it looked like. This super dim condition, it really, literally, when we go into super dim, like Anne was saying, it looks black. You don't see anything. And then what do you have to do when you go from a brighter to a dimmer condition?
Wait 5 minutes?
You got to wait at least 5 minutes. So after 5 minutes, you can actually see enough that you can actually do the task. Although I can say the stick falls really far before you catch it. Sometimes people don't even catch it before it hits the ground, and it's really kind of funny. You start hearing the sticks bouncing off the ground in the super dim condition. Also because the acuity is so low in super dim, that's why we have to make sure there's a really high contrast line on that stick so you can still see something. But so let's see, let's go back to the data, and there we go. This is what we got. Here's subject 1, subject 2, subject 3, subject 4. And what I'm going to do now is just show you what we found. So here is light versus distance. So this is, oops. This is what happened when you looked at light intensity versus the distance fallen in centimeters. And then I just did the little equation, calculating what is the time that's related to the distance fallen. So I can do light versus time. We can look at that here. Back. Let's zoom. So we got this. Basically, as the light intensity goes from the dimmest to the brightest, the reaction time was like 3.35 seconds in the dimmest, but was only a fifth of a second, 0.2 seconds in the brightest. So does this support our hypothesis or not? So we can say, like, we can pick some random person. I can do spin of the wheel. Camille Jouzot. Camille Jouzot, what was your hypothesis for our experiment here?
Her microphone doesn't work.
Oh, okay. Let's spin it again. Chloe Burns, what was your hypothesis for this one?
The brighter the light, the faster speed of reflex because cones process and send images faster than rods. Okay,
and then the one last piece you probably want to have in that is, bright light would mean cones. So you have to have that connection between the light condition to which photoreceptor is active in the light condition and then the speed of those receptors.
Okay.
So the basic idea though is she's predicting faster reaction in brighter light, and does our data support that?
Yes.
Yes.
Yeah, totally, right? Look at that brighter light. There's almost twice as fast that they were able to grab the stick. It was only 0.2 seconds to grab the stick in brightest light, but 0.35 seconds in the dimmest light. So we have really nice results here showing the brighter the light, the less time it took them to complete the reflex. Do you all see that? Yeah?
Yeah.
Yeah. And how can we double check, be sure that, you know, what the effect of practice is? We want to make sure practice was not an important effect in terms of the speed you were doing the reflex. How could we use our data to see how practice affects the timing of the reflex? And this is going to be an important part of your discussion as well. One is, yes, the data supports our hypothesis that brighter light is a faster reflex, but you also want to, our data can also eliminate this source of variability, making sure that the speed of the reflex was not really about practice. So how could we use our data to show the effect of practice on
You would
the
use
speed?
the average.
Say that again?
You would use the average of the 3 trials for each one, and that should.
So that's not, that the average of the 3 trials is kind of individual variation under the same conditions. That's not really kind of looking to see how the more you've done the experiment, the more you've done the task, the better you've gotten or not. Anybody else have a suggestion?
Could you take data from your practice trials?
Um,
Because I know that in the video it had stated that it'd help if you practice before running your real trials.
right, so we do want you to practice a little bit, but by the time you've done your 5th trial, you've done it a lot more than you did in the beginning during those practice ones. So we want to, we'd want to see, like, by the time you've done the 5th trial, when you've already done done the same task again and again and again, you did 3 catches in trial 1, 3 catches in trial 2, 3 catches in trial 4, 3 catches in trial 5.
Oh, do you want to not do 3 at a time and do 1 set and then another set and then another set?
Yeah.
Through all 5 once, then the second time and the third time?
No.
So I think you could just set it up so that you look at the reaction time based on the trials in order that we did them and see if it has a similar downward trend.
So did everybody hear Stephen there? Stephen totally nailed it there. This idea, if here we're graphing what is the reaction time as the light versus light intensity. We could also do a graph. In fact, here it is. This is trial number versus distance fallen. And I can also do, this is trial, like reaction time in seconds versus the light, not light intensity. This shouldn't be light intensity. This should be trial number. Let me change that. I will fix that and upload that onto our website. The thing on your website actually is a mistake there. All right, so let's view this now. So take a look at this. This is trial number 1, trial number 2, trial number 3, trial number 4, trial number 5, and the reaction time. And does there seem to be any correlation between the reaction time and which trial number it is? Again, by trial 5, you have already done this way more times than you've done it in trial 1 or 2. Does it seem to have an effect on the timing of the reaction?
No.
No, yeah, that's a simple answer, no. Here we see that trial numbers going up and down, and it's just kind of looking kind of random. Whereas when we looked at the time of the reaction versus light intensity, a really nice negative correlation. Right,
Yeah.
so this is why we randomize the light. So we could say, oh, if we look at light intensity versus the reaction time, really nice, obvious relationship. Whereas if we look at the practice, the trial number versus reaction time, there really doesn't seem to be a correlation. So this is really nice. This is letting us say, oh, practice really doesn't seem to be making a big difference, especially at least maybe even if it's making some difference, it's very minimal compared to the amount of difference that the brightness of the light makes. So I want to make sure before we kind of log out today, I want to make sure everybody understands that difference, why we have this graph of trial number versus reaction time. Right? This is controlling for practice, right? This is how we can say practice really doesn't seem to have much of an effect on the reaction time, especially when we compare it to this very obvious effect that the brightness of the light has on the reaction time. So does that make sense? Are there any questions about that? Maybe I should say that. Does anyone have a question about what the heck I'm talking about here? In reality, this is something that has very practical implications, right? It means that you have, in fact, I can show you one of the interesting things. Like if you look at, let me, let's share whiteboard. If you look at number of accidents, traffic accidents, and time of day. And you have day, to dusk, to night. The amount of traffic accidents tends to go up at dusk and back down at night. Why would that make sense? Especially given our data. Why would it make sense that you probably have more accidents kind of near dusk? So this makes sense, right? Daytime, something like jumps in front of your car, the reaction time to deal with some visual reflex, right? If you see something jump in front of your car and you have to either swerve or hit the brake, that's a visual reflex. There's some visual stimulus and there's a response. If it's daytime and let's use yellow for the sun, and it's really bright, as opposed to the dusk where the sun is setting, this is going to be bright, this is going to be dim, and what we just saw real obviously on our graph here is your reaction times were literally, not almost 2 times slower in the dimmest conditions compared to the bright conditions. So if something jumps in front of you, you can maneuver twice as fast or have twice as much time to get out of the way compared to the reaction time in dimmer light, right? So trying to avoid an obstacle while you're driving, that's a visual reflex. There's some visual stimulus and there's some response. And here we see that you have kind of twice as fast of a reflex in bright light compared to dim light because the cones are responding way faster than the rods. So if we go back to the whiteboard, and we look at, oh, I just got rid of it. But basically that idea that, you know, day, dusk, night versus accidents. It makes sense that you're going to have more accidents as you get into dusk, because as light goes down, your reactions are slower, you're more likely to actually hit something. Why do you think it makes sense that it tends to come down again at night versus just dusk? What's the difference between driving as the sun is starting to come down versus when you're actually at night?
Your vision adjusts to night.
You know,
Your
the
light
vision adjusted in our experiment, but we're still, rods are going slow. So even though you have, you know, you can see stuff, the speed of the reflex isn't going to be faster because the rods just naturally are slower. So think about being in your car, driving around, and the sun's go.
Headlights.
Exactly, exactly. So what happens when you turn on your headlights?
You're
You
using your
go into cone vision.
Exactly. Now you go into cone vision. Now whatever you're about to hit in front of you is illuminated by your headlights and your cones are active again. So now you actually have faster reflexes because you're using cones because you're seeing things in bright light. You know, it's nighttime, but you've got your headlights to make it bright, so it's now cones again. So, you know, if you think about some of these, you know, cars now actually, you know, when it starts getting dimmer outside, your headlights actually turn on automatically. Or they also have all these kind of daylight safety areas where they have you turn on your headlights even though you don't, you know, but whenever you have your headlights on and there's a bright light, it's more likely that you're going to have faster reflexes because cones are going to respond more quickly. So just kind of on a practical level, you might not have ever thought about it before, but this thing that we've talked about, you know, the fact that cones and rods, you know, faster response, slower response, there's a real practical thing that you've probably never thought about that, and if you're in dimmer light, any kind of visual reflex is just going to be slower reflexes because of pardon me, excuse me, faster reflexes. You know, so just as you move on in life, just kind of being aware, like in dim light, your reflexes are going to be slower than they would have been otherwise. So it's kind of cool. Yeah, so, oh, is that your kid, Jacob?
Just the brothers.
Your brother. So yeah, poor. I feel kind of bad for Corona because Corona's a good beer, and yet now everybody's like kind of connecting Corona to the virus. So I feel kind of bad for those guys. But so are there any questions about all this stuff? This is, you know, This is kind of, I think, an interesting lab, both in terms of what we find. I like doing this because it kind of gives you all a sense more of kind of behind the scenes of what you have to think about when you design an experiment. So you actually have data that you can interpret and data that, you know, if somebody says, how do you know it wasn't practice? It's, well, we actually were careful to make sure we could compare practice versus reaction time compared to the light intensity. And we saw it was the brightness and not the practice. So are there any questions about any of the stuff that we have done in our lab today?
So besides the procedure that we're writing down in our lab notebook, all we need is the data that you're gonna upload and
So
then
I'm
the
gonna,
discussion.
exactly. So
Okay.
I'm gonna upload the data in a few moments. Again, I have uploaded already, but I realized I had a problem in the axis there, which I can fix quite easily. Remember that the way I have designed these spreadsheets is blah, 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 blah. Where is it? Here we go. There's going to be, you know, the first page that has just the numbers, but then I have the little tabs on the bottom. You know, the ones that are going to be probably most relevant for you, light versus time. You're going to want to print this out so you can include this as a figure to support your discussion. You know, practice versus time, you're going to need to print this one out as well and have this as part of your discussion as well. So, and then, yeah, so in your, so for your data, for the raw data, you should probably just include, you know, this stuff here. Include, here we can see in this figure that reaction was, you know, went from 0.35 in the dimmest light to 0.2 seconds in the brightest light. However, we see in the practice case here that from trial to trial, the time did not seem correlated. And then you would write your discussion. And the discussion is just going to be, does the data support your hypothesis? What other kind of interesting things are there? How do you know it's about brightness and not about practice? You know, things like that. So that will be the second part, will be like, you know, writing, putting the data in there and then discussing, interpreting what it all means. And we'll probably have, I'm still figuring out how we're going to be doing this lab book grading, but probably what we'll do is have a second submission where, you know, give you guys time to work on that, but, you know, maybe by early next week, you know, take a picture of your discussion and upload that as well so we can kind of keep rolling along. The lab on Monday is going to be more of a demonstration lab looking at muscle stuff, so you don't have to really think about that ahead of time. So there's no, you know, you should spend time finishing your write-up for the rods and cones lab, but in terms of lab, you don't have to think about preparing anything for Monday. So any other question, Peter? Oh, I don't hear you. Oh, there you are.
Okay. So we are turning in our objective hypothesis and procedure in one end, and then we're also going to be turning in our discussion and data analysis and whatnot
Later.
Okay, so there's no module yet for
There's
that.
no module for that yet. You know, you should spend, you know, the rest of the week or the weekend to make sure that you get that part done.
Okay, and can we draw out the graphs if we can't print them out?
Yeah, if you have, yeah, they're pretty simple graphs, so you could just use the numbers off of the spreadsheet and graph them yourself if you don't have a printer handy.
Okay, cool.
That would work just fine.
Cool.
Any other questions or comments about this all?
I had a quick question about where you will be putting the recordings since you're recording all of the lectures.
So there's two places to find them. If I can show you right now. Booby-dooby-doo. Let me go to share screen, new share. So here in your human physiology thing under, if you go, come on, where does it go? There it is, under Confer Zoom here on the side. If you click on that, there it is. And then, oh, I gotta close, hold on, let me close this thing down. If we go to event recordings here, it actually has the record, like for the last time, if you look, dooby-dooby-doo, recordings for human physiology lecture and lab, chunk, 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 come on. Spinning wheel of death, come on. Come on, come on, come on, come on. There it is. So the M4A are purely audio, the MP4 are video. Streaming is just gonna stream it. The other files you can actually download and store on your computer if you want. So for today, this is for for Monday, we have the recordings. For today, it takes the system a little while to process everything and put it up, but all of the stuff we've recorded today will also be on the menu here, as well as something you can either watch or download. My plan is also to take them and kind of clean them up and upload them onto the YouTube channel. That takes more time. It takes time to do the editing. It takes time to do the mastering. It takes time to do the uploading them and have them processed up there. So, that will take longer, but minimally, if you go onto the Confer Zoom event recordings, you'll always have the raw recordings waiting for you right here. So.
Okay, awesome. Thank you.
Sure. Any other comments or questions before we call it a day? All right, so thank you all for your patience and all as we made it through this first week of remote instruction. And yeah, it's a little better than I was afraid of, and I think it's going to be getting better and better. So I hope you all have a good weekend and stay safe, and I will see you all on Monday morning. And if you have comments or questions about anything, please feel free to email. I also will be available in office hours as well during my normal times, like after class right now, starting at 12:30, as well as on Thursday at 12:30 to 1. No, 11:30 to 12:30. Otherwise, okay, yeah,
Thank you.
All right,
All
take
right,
care.
thank you.
Bye-bye.
Thank you very much.
Thank you, Dr. E.
Thank you.
Thank
All right,
you.
bye-bye.
Bye.
Bye-bye.
Thank you.